All right, so let's go over this exercise. All right, interpret the output of this circuit diagram. All right, we have three inputs, P, Q, and R. Again, just three variables. Truth values, true, false. So you can think of all of these as being, 0, 0, or 1. And then we have the Q signal being split. Right, so Q gets split in two directions. We're going to use Q over here, and we're going to use Q over here. Now, so what I want you to do is pause the video and see if you can figure out what is a symbolic expression for the compound proposition computed by this circuit. All right, pause the video, see if you can figure it out. Now, I'm going to go ahead and go over it. And the way I'm going to show you how to do this is to follow the signals through, and I'm going to use a different color pen to go ahead and keep track of what the signal, what expression represents the truth value of the signal at any given time. So P is coming along, and when it gets to this gate, it's still P. All right, so we'll get back to that. Q comes along here and splits. Here it's Q, and down here it's still Q. Q comes along here, and this second one is going to go into this AND gate. But the first Q here goes through a negation, so this is going to be not Q. Okay, so that means that now we have P, we have the P signal and the not Q signal going through this OR gate. So now we can write this as P or not Q. So that represents the truth value. The truth value is determined by evaluating this logical expression, okay? So now that whole thing is being negated. So what we want here is the negation of that entire expression. Now I'm not going to use De Morgan's law to try to simplify this. I'm just going to write it literally as computed, all right? This is the exact expression being computed by this circuit without any algebraic manipulation applied to it. Algebraic manipulation. You can call it that because anyway, yes, it's basically algebraic manipulation, logical manipulation. All right, so now let's focus on the bottom half down here. We have this R signal that comes along and gets negated here. So now we have not R written there. So now we have Q and not R being fed into this AND gate. So I can write this as Q and not R. There we go. And there's nothing else happening to that. That is exactly the value of the signal that's coming into the OR gate at the end. So now the result over here is going to be the negation of P or not Q, which is that, or this thing, which is, I'm going to put it in parentheses, Q and not R. There we go. That is literally the exact compound proposition that is being computed by this circuit. Now, the question I want to ask next is, can we simplify that? Can't we perhaps apply some of our propositional equivalences from the reference sheet here to sort of like algebraically simplify it down? In particular, we might want to do something with De Morgan's law right here. Let's apply something with De Morgan's law right here. So we have the negation of P or not Q. I'm gonna sort of do a sequence of steps here. Negation, so that first one, negation of P or not Q, can be written as negation of P and the negation of Q. Okay, so that's going to be a double negative right there. And then we have that, or Q and not R. So far, that is by De Morgan. What's next? So now the double negative, we can go ahead and do that. So we have not P and Q, okay? And then we have or Q and not R. That's by double negative. Now, the next thing I'll point out is we have an AND Q in this first term, and we have an AND Q in the second term, and they're combined with an OR. That should sort of set off an alarm bell, because what that is it's basically like a common factor between two terms, similar to that. So essentially, we can use our distributive law. We should be looking at, let's see, the second version of the distributive law. We have P and Q, and then we have a P and R. So we should be able to take the P and pull it out. In this case, the letters are different. In this case, it's not P and Q, and it's Q and not R. So we should take the Q out, and it's going to look like this. Q and, then we'll have not P or not R. That is by the distributive law. All right, so that's pretty good. I think that the one other thing we could do is actually apply another De Morgan's law here, the negation that we have over on each of these two terms here, each of these, the P and the R. We could pull that out by De Morgan's law. Let's see, this is with an or, right? So we're going to pull out the negation and turn that into an and. And then this expression right here, instead of having 1, 2, 3 different operations, 2 nots and an or, is going to go down to having only 2 operations. So this is going to become Q and the negation of P and R. And that's by De Morgan. There we go. So now we should be able to put this together. And this is going to have 1, 2, 3 gates. So let's now take that and translate that back into a circuit. We're going to have Q. Actually, hang on. Let's put these in a different order. P and R together and then Q at the bottom. Because we want to take P and R and put them through an and then invert that, and then do that, and Q. And there we go. That is an equivalent circuit, equivalent to this original circuit that I had written up here. So this demonstrates how you can take the rules of propositional equivalence and you can use them to essentially simplify algebraically, step by step, like this, to something which is much smaller, like a much simpler, smaller expression, which when you translate back into a circuit, gives us a smaller circuit. This is going to save space on your circuit board. It's going to save time in your computation. Like your computer will literally run faster if it has simplified circuits than it would if it was using more complicated circuits. So all of this is playing a role in optimizing the circuit board that you might design, for a computer to run on. Yeah, this is really basic, basic application, and this is stuff that's been around for decades. These are ideas that have been around for decades, but this is really like fundamental to the design of computers. So I think that'll do it for this one.